know what's really cool? Space. It's got celestial bodies like constellations, galaxies, black holes, and most importantly, us. Speaking of us, on Earth, we have 3 dimensions: length, width, and height. But in space, there's something more. In Albert Einstein's special theory of relativity, he suggests that time is linked to space in a complex system. The result of this is that it is impossible to move in space without subsequently moving through time. This is time dilation. Now, how do we know that all of this is true? Let's take 2 flawless atomic clocks that are perfectly in sync. We take one clock and send it on a high-speed space trip. The other clock remains stationary on Earth. Now the spaceship returns. The clock on board shows that less time has occurred than the one on Earth says. Thus, a moving clock appears to run slowly when observed by a stationary viewer. Once the space trip clock returns to Earth, it records time at the same rate, as dilation only occurs when the clock is in motion relative to the second clock. But why is this? Let's re-explain the hypothetical, but this time focusing on the clocks. The flawless atomic clocks I mentioned before are light clocks. They measure time by sending a beam of light from the bottom plate to the top plate, where it is then reflected back to the bottom plate. The fact that light is used is very important. The speed of light is constant, regardless of its motion. The 2 clocks are synced, and it takes 1 second for the ball of light to bounce to the top and then be reflected back down. This is what the clock looks stationary. Now we place the clock on our spaceship, and it looks the same to someone on board. However, when the spaceship and clock are in motion relative to a stationary observer, the observer sees something different. To the observer, the clock has moved further, even though it travels the same amount of time. In this example, the beam traveled farther, and the speed remained the same because the speed of light is constant. Speed is equivalent to distance over time, so the only way that speed was able to remain the same when the distance was increased was for the time to also increase, causing time dilation. Traditionally, at a normal speed in space, the effects of time dilation are so small they go unnoticed. For a noticeable dilation, a person would have to move around the speed of light. However, I want to show the effects of time dilation through something known as the twin paradox. In this hypothetical, we have a set of twins, Eloise, who will have stay on Earth, and Skylar, who we will send to space. Before Skylar leaves on his space trip, he's the same age as Eloise. However, he won't be once he returns. Skylar goes off on his space trip. Relative to Eloise and time on Earth, Skylar's time appears to be running slow. When Tyler looks back at Earth, their time appears to be moving slower relative to his because he believes he is stationary according to his clock. Because time ticks slower for Skylar on his ship relative to Eloise on Earth, when he returns, he will be younger than his twin Eloise as he is being compared to Earth time. The twins might disagree on who is moving and who is stationary during the experiment, but because Skylar is being compared relative to Earth, he must have moved through time. The real question is, do you think they're really twins anymore?